morning, mindsetters, physical scientists, grade 12s. I hope you guys are ready. We're in studio. We're ready to help you guys with paper 1 prelim questions. I am Looney, and joining me in studio is TK. How are you, TK?
I'm good. How are you?
I'm good, thank you. So what are we doing for the mindsetters today?
Well, we've got a packed revision session here in physics, and we'll be looking at electricity, circuit calculations to be precise, and we'll be looking at waves as well. We'll be looking at diffraction and something around momentum as well. And if time allows us, we may also look at some projectile motion.
Oh, wow.
Yeah.
Mindsetters, you heard it. We've got a mixed package here for you guys. All physical sciences. Don't forget to hit us up on Twitter at LearnExtra, and our Facebook page is facebook.com/LearnExtra. We are facing technical difficulties on learnextra.co.za/live. So make sure you check our Facebook page for the notes, guys. We will post all the questions as we're going along during the lesson. So make sure you are glued to the Facebook page as well as on your screens, and you're listening to TK as he explains this lesson. So TK, over to you.
Okay, now let's just get ahead. We are looking at physics section, as I've said here, and we're looking at circuit calculations as well as diffraction patterns. From there, we may also have time to look at momentum, but I'm not so sure if we'll have time to look at some questions here that we have based on projectile motion. But quickly, let's just have a look at this question here. Our first question for the day is from a prelim paper from KwaZulu-Natal. Okay, so those of you who are from down there, you should know that we have taken your paper today, and we are actually talking to the whole nation about it today. Now, it says here in the circuit diagram below, all right, L1 has a resistance of 3.8 ohms, and L2 has a resistance of 2 ohms, and L3 has a resistance of 3 ohms. Okay, the switches S1 and S2. Now let's just have a look at that. The switches S1 and S2, just pardon us for the typing there, that is actually merging and getting together, getting on the way here. Those two switches are now open, all right? And the reading on the voltmeter is 12 volts. Now, if you are told that all the switches are open and you've got 12 volts, immediately you must know that this is actually the EMF of your battery. Okay, good. Now, the connecting wires and the ammeter have negligible resistance, all right? The battery has an internal resistance, small r. Okay, as you can see on the drawing down here, there is the small r. We're talking about the internal resistance. Okay, now let's just go through these questions, all of them, before we attempt answering them. We'd have a chance to look at that. When only S1, switch 1 is closed, with S2 still remaining open, the reading on the voltmeter becomes 9.5 volts, and that tells you immediately here that we're going to talk about lost volts as well, because we started with an EMF of 12 volts. Now we are told when that switch S1 is closed, we are down to 9.5 volts. A, calculate the total resistance of the circuit. Okay, now I need to give you tips here as well to say, once the question tells you calculate the total resistance, it means you need to check on your diagram, your circuit diagram, whether you've got a parallel section and a series section. So you'll need to start with the parallel section, finding the equivalent resistance of the parallel section, and then you add it to the resistance of the series connection, so that you now have answered the question that says find the total resistance of the circuit. Okay, now B, calculate the internal resistance R of the battery. For you to get the internal resistance, if you know what the lost volt is and you also know what the total current is, you can quickly get there. So that's one way of knowing immediately what to do when you are faced with a question like this. Of course, we're going to do it, so you're going to see it right now. Now, switch S2 is now closed, also closed now, and all light bulbs continue to burn. Will the brightness of L1 increase, decrease, or remain the same. Okay, use an appropriate equation or relationship to explain your answer. So we're gonna look at that as well. Now, moving on. This is the question 1. All right. Let's now start with the first question. The first question that says, when only switch 1 is closed, whilst switch 2 is still open, the reading on the voltmeter is that, and then we are to calculate the the total resistance of the circuit. Okay, now let's have a look at that. We were told that this L1, okay, the resistor or resistance of L1 is what? L1 is 3.8 ohms. Okay, and then L2, let me write here, L2 is 2 ohms. Then L3 is what? L3 is 3 ohms. Okay, so that's what we have here. And we are told that, or the question wants us to find the total resistance. Now you would see that L1 is in series to the circuit. So that is a series connection. Now L2 and L3 are the parallel connection. Okay? So for us to get the total resistance, we need to match the two. How do we do that? Let me just show you now. Okay, now let's start with the parallel connection. Like I said, RP, 1 over RP should be equal to 1 over R1 plus 1 over R2. Now I only have 2 resistors that are in parallel, so I would have it in that way. Okay? Now their values, L2, which is R2 here, will be 2 ohm, L3 will be 3 ohm. In fact, I can easily say that this is my R2 and my R3, because my R1 will be for the L1, light number 1. Okay, so I would continue here and say, all right, this is 1 over. R2 is 2 ohms, R3 is 3 ohms. Can then work this one out quickly. All right, we can then work this one out quickly. How do we do that? The LCM here is 6. 2 to 6 is 2, 3 times 1 is 3, plus 3 to 6 is 2 times 1 is 2. All right, so what do we have at the end? 1 over RP is it's 3. Sorry about that. Okay. So 1 over RP is 5. That is 3 plus 2, 5 over 6. Therefore, your RP over 1 is 6 over 5. And that gives you what? That gives you 5 to 6. It goes once, remainder 1. 5 to 10, it's 2 times. So now you know that the equivalent resistance for the parallel connection is 1.2 ohms. But I haven't answered the question at this point. The question wants me to get the total resistance. Now, total resistance R, okay, total resistance RT would be equal to the series connection, which is given to me here. What is the value for the series connection? I have this resistor here for L1, which is 3.8 ohms. Okay, so that will be 3.8 ohms plus the 1.2 ohms. And what do I get here? This is 4, 5. So I've got 5 ohms as my total resistance for this circuit here that we're looking at now. So that is how you would answer this question here. That's how you would answer this question. Now, moving on to the next part of the same question, which is question number B. It says, calculate the internal resistance R of the circuit. Now, how do I do that? Okay, now, to do that, I will need to get the total current in the circuit. And how do I do that? Because I've got the potential difference. I've got the 9.5 volts, remember, that is given to me when switch 1 is closed. I also have the total resistance of the circuit, and from that I can calculate the current first. Okay, so I can say, okay, total current in the circuit will be given by V over R. Okay, and what is V? V is 9.5 volts divided by total R is what we have just calculated now, and we found it to be 5. And what is this here? All right, now 5 to 9, it will go once, and just use a calculator quickly without wasting time here. So we've got 9.5 divided by 5. All right, and what do we get there? That is 1.9 ohms. Okay, so that is 1.9 ohms. I mean 1.9 amps or amperes. Sorry about that. That is the unit of measurement for current. And once I've got these, I can use a quick way of finding my internal resistance, because I now have the current. I've calculated it. I found it to be 1.9 amperes. So if I have that, I know I can get V lost from the information that has been given to me, and I know that that V lost will be given by total current times internal resistance. I can get that. Now, how do I get the V lost? You would remember in the question we were told at the beginning here, we were told that when S1 is closed, I've got 9.5 volts as a reading on my voltmeter here, but the battery is given to me as having an EMF of 12 volts. So that difference, the difference between 12 volts and 9.5 will give me my lost volts. Okay, so I can therefore come to the point where we are here and say, all right, this will therefore mean that my V lost will be 12 volts minus 9.5. Okay? This should be equal to 1.9 times internal resistance. Now, what is 12.5? I mean, what is 12 minus 9.5? That gives us, we look at it, that gives us 2.5. So the lost volt is 2.5, equal to 1.9 internal resistance. So my internal resistance in this case will be given by 2.5 divided by 1.9. And what do I get? Can quickly make use of your calculator again here. Let's just bring it on. So you've got 2.5 divided by 1.9. Okay, divided by 1.9. And what do we get there? We're getting it to be 1.32. Okay, 1.32 ohms. That's what we're getting there, 1.32 ohms. Okay, so 1.32 ohms is the internal resistance of the battery. Okay, so let's move on. Right, now the next one, still on question number 1. Let's have a look at this one, number C here. Number C here says, when only switch 1 is closed while switch 2 remains constant, that is the readings we're getting, okay? Now switch S2 is closed and all the light bulbs continue to burn. Will the brightness of L1 increase, decreases, or remain the same? Use an appropriate equation or relationship to explain your answer. And I'm just going to stick to the relationship that will be quicker for you to understand and see. All right, now let's just look at this here. Go back to the circuit. If you look at this circuit here, what the question is saying is that if the switch here is now closed, remember this one was closed long time ago. Now, both the switches are now closed, and all these bulbs continue to have some light, okay, to burn. What will the effect of closing S2 have on the brightness of light bulb number 1? Okay. Now, if you look at this, you would see that the ammeter is connected in parallel. Okay? It's part of the parallel connection here. This connection here. Use a different color for it. This connection here. Now, because of that, this little resistance of the, let me use a very small r to just explain that. That minimum resistance of the ammeter, which is negligible, I mean, given where we started from, you would see that it would have an effect. Let's talk more about this when we come back from the break.
All right. Mindset says we are going to take a very short break. Don't go anywhere. We will be back straight after this.
Okay.
Welcome back, Mindsetters, from that very short break. I hope you guys are still on par at TK and you learning with him as he explains everything. So I won't take any more time. TK, over to you.
So thank you. Let's move on. And I was still on question number C here, and we trying to explain what happens here, because you are told that switch S2, okay, switch S2 has been closed now, and all the 3 bulbs continue to burn. So L1, L2, and L3 are continuing to burn. Now, what will that effect have on the brightness of L1? That is what the question is. And I was saying to you that if you look at this here, the ammeter is connected in parallel with this section here of the circuit. Now, if it is in parallel there, it tells you that for you to get the total, the parallel resistance here, the total parallel resistance here, you would need to include the resistance of the ammeter. And what happens is that because the resistance of the ammeter is so small, okay, let me write down what I'm saying here. Okay, the resistance of the ammeter is so small. Resistance of the ammeter is very small. Okay, that's why usually you are told this resistance of the ammeter is negligible, so it's very small. Now, in a parallel connection, if you put all the parallel connection resistances together, when you work it out, at the end, the resistance of the parallel section is always smaller than the smallest resistor there. So the RP, when you calculate, it's always smaller than the smallest resistance in that section there. The smallest resistance. Okay, so if this is what it is all about, it means that the total resistance there becomes smaller, therefore making the total resistance of the circuit even smaller. So let's just say something about that here. We would therefore say that because the RP has become very smaller than the smallest resistance, then the total, all right, sorry about that, then it would mean that the total resistance of the circuit, becomes effectively small. Okay? Effectively small. And by this I mean it is going to affect the total current of the circuit. Okay? So total resistance become effectively small. Okay? Therefore, the current, remember, Therefore, the total current, in fact, I should be writing total current there. Therefore, the total current I of the circuit increases. Okay? And how do we know it's going to increase? Due to the fact that we know that the total current is given by I equals V over R. And remember that V is not changing. What has changed effectively is R. And therefore, if you make the denominator smaller here, you are making this value here bigger. And therefore, total current going up, increasing. What does it mean for light bulb 1? Look at it. Light bulb 1 is connected in series, and therefore, total current I in the circuit passes through L1. So because this I has now become greater than before, it means that L1 becomes more brighter. Okay, it becomes more brighter than before. It becomes more brighter than before. So that's what we have there. So in answering this question number C here, we would therefore start by saying that the brightness of L1 increases. Why? All the explanation that I have given to you there will be the explanation for why the brightness of L1 increases. All right, now let's move on. We're coming to question number 2. All right, question number 2. And how do we right, so there we go. So we have question 2 here, adapted from the prelim paper, okay, from Houghton. All right, GDE, paper 1, question number 8. The circuit diagram below shows a battery with an EMF of 24 volts. And we don't know the internal resistance here as well. The ohmic resistors R1, R2, and R3 have resistances as shown in the diagram. So that will be part of the diagram. We'll see that now. Okay, the resistance of R4 is not known as well. Okay, when switch S is closed, the reading on voltmeter V2 is 22 volts. Now let's look at where S is. There is S. All right, when that is closed, the reading on voltmeter V2, this one here, is 22 volts. But then down here, more information is given to us. We are told that the EMF of the battery is 24. And immediately we can tell that there is a lost volt. There is V lost of 2 volts there. Okay. Then that is the question. Let's just have a look at number 1 here. Now, we are told in that question that these resistors are ohmic resistors. And immediately there's a question around that. We are asked to define what is meant by an ohmic resistor. Okay? This should be simple to explain. You don't have to define Ohm's law, but if a resistor obeys Ohm's law, that resistor would be an ohmic resistor. So you would write here that ohmic resistor is one that obeys. It's one that obeys Ohm's law. It obeys Ohm's law when temperature is kept constant. Remember that Ohm's law works out only when this condition is met, that the temperature remains constant. Okay, so that's what we have. So if you have a resistor that would obey Ohm's law even when the temperature, when the temperature is kept constant, then that resistor will be an ohmic resistor. Ohm's law says that the current in a conductor is directly proportional to the potential difference across its ends, okay, provided temperature remains constant. Okay, so that's what it is all about there. Now, moving on, still on question 2, coming to the next question on question 2. It says here, calculate the following, all right? Calculate the following. We are to calculate the equivalent resistance of the parallel combination, so parallel combination, and we also have to find the magnitude of the current through resistor R2, okay? And then resistance of R4. Okay, now let's have a look at that. Now, before we start looking at that, let's just have a look. Where is your parallel connection? This is your parallel connection section. Okay, that is the parallel connection there. We are to find the equivalent resistance there. And how do we do that? Let's see if I have space here to do it. Okay, I don't. Let's just go back here, and then we will have more space here and do that problem. So this is B, Roman figure 1. All right. So we know that for parallel connection, 1 over Rp would be equal to 1 over resistor 1 plus 1 over resistor 2 plus 1 over resistor 3 plus 1 over resistor 4, depending on how many it's given to us. But then now, if you go back to the circuit here, these two here, these two resistors, these ones, are in one line. So it's like one resistor, okay, which is in parallel with the bottom one. Okay, so what we're going to do is to say we're going to have 1 over 24 there, because 10 plus 14 is 24, plus 1 over 12. That's what we're going to do. Right, so that equals 1 over 24 plus 1 over 12. Okay, this is still 1 over Rp. That then equals, LCM here is 24. 24 ones, 1 times 1 is 1, plus 12 into 24 twice, 2 times 1 is 2. So you have got 1 over Rp equals 3 over 24. Okay, 3 over 24. Therefore, Rp will be equal to 24 over 3. I'm following every little step so that even those that didn't get it at the beginning when you were taught, you see what's happening here. So that tells us 8 ohms. So we've answered that question there. Going back to it, looking at the next one. It says, find the magnitude of the current in resistor R2. Now you go back to resistor R2. Okay. Now, if you look at where R2 is, there is R2. We are told we know the current that passes R1 here, which is 0.9 amperes. Now, let me just work it out here so that you refer to the table, you refer to the drawing, and you can see what I'm doing here. This one here, 12 ohms, is half the 24 ohms for the combination of the top parallel, the top resistors that are in parallel with the 12 ohm resistor. So if I've got 0.9 passing through here, it means up here I would have half of what is passing, sorry about that, of what is passing through this resistor here. Why? Because this one is half of that, and these are connected in parallel. So I would say that current 2, which means current passing through resistor 2, would be half of the current passing through resistor 1. Okay? And that would mean I've got half of current passing through resistor 1, 0.9. So that tells me that I would have 0.45 amperes passing through the 10 ohm resistor here, which is the R2 here. Now, somebody might be asking, why, sir, are you saying it's going to be half and you're referring to 24 ohms and yet that one is 10 ohms? Now, look, the current passing through, the current passing through R2 is the same current passing through R3 because they are together, they are in series, okay? But then this series combination is in parallel with another resistor, okay? So that's what is happening there. Next, find the resistance of R4. Now, finding the resistance of R4, you go back to that, you see here, this is the R4 we're talking about, this one here. All right, for me to find the resistance of R4, it will be easier if I find what V is there, okay? If I find what V is there, it will be much easier. And how do I find what V is there? I now have, if you like, I now have the total current here that is passing through R4. How do I get that total current? It is this current here, 0.9 ohms, 0.9 amperes, plus the current passing through there, which is we have found that out now, is 0.45 amperes. These two must give me the current passing through R4 there, okay? And therefore, I can be able to say that if I calculate for V there, all right, okay, let's find what V is going to be there. Now, V is equal to I times R, okay? I now have the current there. Let me see here from the information that I have here. V2 is 22 volts when the switch is closed, okay? And resistor R1 is 0.9 ohms. It's 0.9 amperes there. So, okay, we also have run out of time for now. So we're going to leave it here, and when we come back, we're going to start from here and close this question very nicely. But like I said, we now have the total current, so that will help us find what R4 is.
Okay. Mindsetters, let's take a very short break. Don't go anywhere. We will be back straight after this. Welcome back, Mindsetters. I hope you guys are still with us and that you're still tuned in with TK. So TK, over to you.
Thank you. Let's just proceed here. Remember, we are trying to find out what the resistance of R4 is here. Okay. Now, I said because we now know what the total current is, it will be much easier to get what the resistance is for R4. How do we do that? I think some of you might already have come up with ways of doing this. You can see that for us to do that, we will need to know what is V here. Okay, so what is V on your parallel connection here? What is V here? Okay, so what is V there? Once we get V there, then we will know what V4 is here, which is the potential difference across the R4 resistance, okay? And therefore, we will therefore need to say, okay, to do this, okay, that is, I think, Roman figure 3. To do this, we'll therefore say the potential difference across the parallel section should be given by the current, all right, in that parallel section times what? Times the resistance of that parallel section there. So that would help us find that, the VP there. That will be equal to, remember, we calculated for the current. One current is given to us, but the other, we had to calculate for it. We know that the current here is 0.9 amperes, and then what we calculated as the current passing through the top resistors is 0.45 amperes. So what we will do here is to say, okay, this would be 0.9 plus 0.45 times RP resistance. Remember what we worked it out to be? We worked it out to be 8 ohms. And therefore, you work this out. This is going to be, let's just use your calculator quickly. Okay, so when you come here, you know that you've got this part here. You will need to start from that part, okay, before you multiply, because it's inside the brackets there. So you will say 0.9 plus 0.45, okay, you get your answer, and that must be multiplied by 8. Okay, so we're getting the V around the parallel combination. So VP equals 10.8 volts. Okay, 10.8 volts. Now, if VP, you go back to this here. If VP here is 10.8 volts, yet the external potential difference is 22 volts, because when switch S is closed, V2 gives us 22 volts, but you started from 24. Remember, that's your EMF. So if the external potential difference is 22, and part of it, which is 10.8 is there, what will be the remaining for that part there? This one here will be 22 minus 10.8. And what is 22 minus 10.8? That should be 11.2 volts. Okay, I think I got that one right. 11.2 volts, yes. Now, if that is 11.2 volts, then we can find the resistance of that resistor R4 there. How do we do that? R4 will be equal to V across 4 divided by the total current, because remember, that is the resistor through which the total current in the circuit will pass through. It is the only resistor in series, as you see it there. All right. Now, this then would be given by, what is this one here? It's 11.2, that is V4, divided by 1.3. How did we find the total current to be? We found it to be found that current to be 1.35, isn't it? Okay, we'll just work it out quickly again. Okay, right, so let's go to the end. Okay, let's just work it out quickly. So it will be 11.2 divided by 0.9 plus 0.45, and that should give us okay, come on, right. Okay, so we have 0.9 plus 0.45. We've worked this out earlier, so 1.35. Okay, so that's what we have. So 1.35, and you work that out again, bringing in your calculator. You've got 11.2 divided by 1.35. Okay, and what you get, you're getting 8.296, and that rounded off to 2 decimal places, it will be 8.30. So this is 8.30 ohms. That is the resistance of the resistor number 4 there in your circuit. Okay, it's the resistance of this one, as we are asked to do. Okay, I hope you've got that right now. Let's see if we can have some more time to do others. Let me see here. Yeah, we actually should be going to question number 3. But let's see, do we have a few questions that are related to what we've been doing now?
Yes. So Godfrey is asking, what if they say calculate total current without having R2 on the parallel circuit?
Without having R2 on the parallel circuit, I'm not so sure which one he would be referring to, or without having R2. So he would be referring to this one.
Yes.
Okay. Godfrey, if you didn't have R2, I just think that you are saying you only had R3 here and R1 here, which perhaps R3 would have been R2. So say that was not there. It means that what we are going to do to find to find your parallel resistance there, the total parallel resistance, what you would have done, it's just simply this. You would have just said 1 over Rp would be equal to 1 over what would be there is 14, and the other one would be 12. That's all you would do. Okay, but because these two are tied together, Godfrey, you have to add them together because they are in series in a parallel setup. You still have to add them. But then if, like you're saying, if R2 was not there, that was going to be very simple. You would just do it like that. Okay, good.
One more question.
One more.
No, 2 more.
Okay.
Brilliant is asking, what's the difference between effective and total resistance?
All right, brilliant, effective and total resistance. I would say that effective resistance is, if I want to know what will be a resistor that will replace all the resistors in parallel, a single resistor, what will it be? Then that becomes the effective resistance of your parallel connection. But when we say total resistance, we mean that you would need to add all the resistances together from your effective resistance of your parallel section to your resistances of your series connections. So total resistance means you're talking about the resistance of the whole circuit there, and usually, of course, external circuit, because we normally wouldn't include the internal resistance, and we know how to deal with the internal resistance from the V lost and other things. Okay, so that is how you should differentiate between the two.
All right.
Okay.
And then last question, Masemodi is asking, how do you calculate the internal resistance of a circuit if there is a parallel connection and you don't have a reading of one resistor?
And you've got a parallel connection, you don't have a reading of one.
And you don't have a reading of one resistor, and you're asked to calculate the internal resistance.
Okay, in that case, if you don't have a reading of one resistor and you are to calculate the internal resistance, I believe that they would have given you other information. For example, they would have told you that the battery has got an EMF of so much. When that switch is closed, then it decreased to so much. So you can work it out from your lost volt. That's what it means. Or if they don't do it that way, they can actually tell you to say, all right, the total current of the circuit, it's so much. Or they put an ammeter that is in series with the circuit that will be telling you the total current in that circuit. And from the total current, you can then be able to work out your internal resistance should you know the V lost and the total current. Okay. So that's how it should be done, or it should be worked out. They can't ask you to calculate for something and not having given you enough information or some other information that will lead you to getting that particular answer. Okay. Well, we need to move on quickly now. I just want to try and see if we can't do this question here. Let's come to this one here. We have question 3, and we're switching completely from electricity, from circuits to waves. Okay? Diffraction patterns. Okay. It's our question 3 for the day, and it says the diagrams below show the diffraction patterns. So we've got diffraction patterns for a yellow light and a blue light. Okay, yellow light has got a wavelength of 582 nanometers, this one with the blue one with 460 nanometers. Okay, they are both passed through the same slit in turns. Study the diagrams carefully and answer the questions that follow. Okay, so we've got diffraction pattern number A and diffraction pattern number B. Question, state Huygens principle. Okay, let me see if I have got, yes. Stating Huygens principle, all you need to know is that these, you've got wave fronts, and points on wave, or on a wave front, points on wave fronts would always act as secondary sources They act as secondary sources of wavelets that proceed in a forward direction. Okay, so that is more or less the way you should state the principle, Huygens principle. Okay, so these points on a wavefront act as sources and of secondary wavelets. So you've got waves and waves and waves moving on, proceeding in a forward direction. Okay, next. Okay, so we're coming to question number B here. It says, which diffraction pattern represents the yellow light, A or B? Justify your answer. Now, yellow light, if you check, yellow light has got a much larger wavelength compared to the wavelength of the blue light. Okay? So, with a larger wavelength, the pattern of the diffraction pattern of yellow will be B. Why? Because, look, from this equation here, we can tell, let me just write it down. Okay, this equation here, we can tell that the diffraction pattern, the largeness of that diffraction is directly proportional to the wavelength lambda. Okay, so if you see it bigger, it tells you that the one with a bigger wavelength will be the one that gives you that particular diffraction pattern. So that's why I went for B there. Okay, that's why B is the answer. So that's how you justify it. All right, so moving on, let's see if we can do number C with a little time that is left for us. Number C says, calculate the position of the first dark band for the blue light if the width of the slit is 5 by 10 to the power minus 6 meters. Now here it means you would need to use that equation that I've just written down to justify what I was explaining earlier on there, to find the angle theta, okay, where A is the size of the slit, lambda, of course, is the wavelength, and M is the number of your dark band. So let's find out what sine theta is going to be here. So sine theta is going to be, we are told, the first times the wavelength, and we're talking about the blue light. So blue light's wavelength is 460 nanometers. We don't work in nanometers, we work in meters. So you'll need to convert this into meters. 460 nanometers in meters, it's going to be, so that's 160. You'll have to multiply this by 10 to the power nano to the power 9. So when you do that, you have converted it from nanometers to meters. You're dividing that by the size of the slit, A. And what is A? A is given to us as 5 by 10 to the power minus 6 meters. So this is 5 by 10 to the power minus 6 meters. That then works out to be, we bring out our calculator, okay, and we say, okay, what we have there is 1 times that is going to remain as that, so it's 460 by 10 to the power, let me just do it this way. So it's 460 by 10, 460 by 10 to the power minus 9, divided by 5 by 10 to the power minus 6. Then the answer is 0,092. So I've got 0,092. But remember, this is the sine of the angle theta. What I want is the angle theta, which will be given by, let's just quickly work on it. It's going to be given by the sine inverse of 0.092, which is going to be, now let's just work it out here. So the sine inverse of 0,092 2. Okay, what do I get? And the angle is 5.28 degrees. So theta is equal to 5.28 degrees. That is the position at which we're going to see the first dark band. Okay, now let's see. Do we have a few questions?
Let us check quickly.
Few questions, so we can close.
Let's take a break shortly and then.
All right, that's fine. Thank you.
Mindsetters, let's quickly take a break and then we'll see you straight after this.
Okay.
Welcome back, Mindsetters, from that break. I hope you guys are all refreshed in your minds and you're ready to write down the notes and you taking in everything that TK has been teaching you, because he's quite a good teacher. So over to him once again.
Thank you. Let's proceed. And like you know, we have been talking about the diffraction patterns before the break, and this is the question that we had, and it's based on these two diagrams here. And there's something that I want to explain to you quickly, because I can see that some people might get confused here, because the question talks about finding the position of the dark band. I'm referring to especially this question C here that says calculate the position of the first dark band for the blue light. Okay, so the first dark band for the blue light if the width of the slit is that. So we have calculated for it and we found it to be at 5.28 degrees, okay, at that angle. Now, if you look here, you would see that this part here is black and that is black here, and some people might think that is what we are referring to. No, the diagram here had to be made white because our smartboard has got a black background color there, you see, for us to be able to write so that you can see what we're writing down. So basically, it is this white point here, it's these white points or lines there that are being referred to, that are serving as the dark, see them as dark bands. We made them white so that they can be visible from the body. If they were on your question paper, which is of course on a white sheet of paper, these would have been drawn in black. All right, so that is what we were referring to here when we're talking about the dark band here. So instead of dark, it's that bright. So don't get confused there. Right, now moving on. We are moving to question number 3. Okay. We're still on question number 3, but coming to question number D on it, which says, if the width of the slit is made smaller, okay, that's the key word here, than the 5 by 10 to the power minus 6 meters, how will the diffraction pattern above, or the diffraction patterns above, be affected? Give a reason for your answer. Okay. Now, look, if you looking at the diffraction pattern, you need to understand how they are going to happen is dependent on two things. It depends on the wavelength of the electromagnetic radiation that we're looking at, or that particular color that we're looking at, color of light. 2, it also depends on the size of the slit there, okay? So that diffraction pattern will depend on those two things. Depends on the what? On lambda, and they also depend on A. So if you make A smaller, what will happen? The diffraction pattern sine theta is directly proportional to wavelength, but this sine theta is inversely proportional to the width of the slit. So if you make this slit smaller, what are you going to do to the diffraction pattern? The diffraction pattern is going to spread out more bigger, okay? So it will become larger. So the diffraction patterns, your answer here would be that the diffraction pattern, the diffraction patterns will become larger, okay, or bigger. Why? Because this diffraction pattern is inversely proportional. So inversely proportional. The diffraction pattern is inversely proportional to the size of the slit. Okay, the size of the slit. Okay, so that is how you answer that question. It has to become larger, the diffraction pattern, because if you make this one smaller, which is inversely proportional to the diffraction pattern will have to become bigger. All right, now let's move on to question number 4. All right, question number 4, and this we're taking from the GDE paper again. This is the Gauteng paper 1, question number 3 for 2012. Right. It says here, and you can see immediately that we're switching here. We're switching to mechanics. We're switching to momentum. Now, here is a tip for the exam. It always becomes easier to understand the question and to understand what to do if you start by reading the questions first before you read the information. In other words, you read all those questions together, trying to find out what it is that they are asking you to do. Okay? And that preempt to you that in the information that is given to you, there should be 1, 2, 3 that I need to take serious consideration of. Okay, now let me just do that here so that we can be able to see what I'm talking about here. Let's have a look at it. Here is the momentum question from GDE September paper 2012. When I look at this, okay, I've got questions here, and I've got also the information here in terms of the cars. Okay, the cars are saying something else, but let me just show you the questions only. Question number A, it says, calculate the magnitude of the velocity of the delivery van immediately after the collision. So there shall be a collision here. Now, if they say I must calculate the magnitude of the velocity after the collision, it means they would give me the velocity of the delivery van before collision. I would also have the velocity of the other vehicle before collision, and I would also have the velocity of the other vehicle after collision. Okay, because for me to get that one, I need all those information. And of course, I'll be needing the masses. Calculate the change in the kinetic energy of the system. Now, calculating the change in the kinetic energy of the system, it means that I would find the kinetic energy of the system before collision, then the kinetic of the system after collision. Okay, so that I can find out what was the change in that kinetic energy. Right, so that these questions are leading me already. What type of collision is this? Ride only, elastic, or inelastic? Of course, the change in the total kinetic energy of the system will tell me whether this collision is elastic or inelastic. So that is sorted for now. So already the questions are actually leading me to say, when I approach this question, what must I look for in that information that is given to me? If the collision lasts for 4 seconds or 0.4 seconds, calculate the magnitude of the force that the delivery van exerts on the car. And of course here, I need to be talking impulse. I need to bring in F delta T equals M into V final minus V initial for that particular vehicle, which is the delivery van in this case. All right, now let's go back. So this is a tip that I am freely giving to you now to say, read the questions first. They will lead you to what you should look for in the information so you can answer your questions brilliantly. Okay. There is the question. A delivery van having a mass of 500 or 5,000 kilograms is moving towards the right at a constant velocity of 10 meters per second. Okay. So the information here, I mean the diagram here helps me to get this information here as well. The delivery van collides head-on with a car of mass 2,000 kilograms, moving at a velocity of 15 meters per second towards the left. Immediately after the collision, the car moves at a constant velocity of 5 meters per second towards the right. Okay? So I need to put the after part here. All right? This one, immediately after collision, we are told this one moves at, so V final for the car is 5 meters per second to the right. Okay? Now, calculate the magnitude of the velocity of the delivery van immediately after the collision. Okay? And how do we answer that, or how do we do that? Let's just extend this page here. To do that, we need to make use of the principle of conservation of linear momentum. Okay? That tells us that total linear momentum in a closed system remains constant in both magnitude and direction. So I would say that, okay, the momentum, okay, let me start here so that we have some order in the way we're doing it. Total momentum before would be equal to total momentum after. Okay, that is the principle. So this means that the mass of the delivery van times the velocity initial of the delivery van plus, okay, so I must come back here and say ID, delivery van, plus mass of the car times the initial velocity of the car before. Okay, this is all before. Let me just, don't have to even say that, because once I say initial, I mean before. All right, so that should be equal to mass of the delivery van times the velocity final of the delivery van plus mass of the car times the velocity final of the car. Okay? Right. Now, from the given information, what do I have? I also need to take direction into consideration here. So let me say, because I'm dealing with velocity, let me say to the right, let's make it to be positive. So I'm told here that the delivery van, okay, is moving to the right with at 10 meters per second. So I would say that the mass of the delivery van is 5,000 times 10, positive because to the right, plus mass of the car 2,000 times minus 15 meters per second to the left equals mass of the van 5,000 times velocity final of the delivery van plus 2,000 times, this time the final velocity of the car is to the right, so it's positive and it's given as 5 meters per second. Okay, so we can work this out. This works out to 50,000. This works out to be oh, where's my calculator? There it is. Okay, so 2,000 times 15, but it's minus 15 here, so this is minus 30,000. Minus 30,000. Okay, this should be equal to 5,000 V final delivery van plus 2,000 times 5, that's 0, 0, 0, 10. So that is 10,000. Okay? Therefore, 5,000 V final D should be equal to 50,000 minus 30,000 is 20,000. 20,000 minus 10,000 is 10,000. Okay? Therefore, V final of the delivery van would be equal to 10,000 divided by 5,000. And that should be what? Okay, you can go if you want to. Okay, so you've got 10 divided by 5, that is positive. It gives us positive 2 meters per second. Now, because it's positive, it means it is going to the right. Okay? It means it's going to the right. So that is the answer for number A. Coming to number B, calculate the change in the kinetic energy of the system. Okay? Now, kinetic energy of the system, how do we calculate for the kinetic energy? The system means both the cars. So EK for the delivery van will be equal to what? Half mv squared. That will be half times the mass is 5,000 times it's moving at 15. That is squared. Okay, half of that is 250. Let's just work it out using a calculator quickly. So we've got 15 times 15 times 5,000, okay, divided by 2, half of that. I've got 562,500, so 562,500 joules, okay? Then EK for the car, again half mv squared, so it will be half times 2,000 times it's moving at 10. Okay, so it was 10 meters per second. Let me be sure about that. 10 meters per second. No, it is, in fact, the van is the one that is 10 meters per second. So I made a mistake here. So let's quickly sort this out. So this is actually 10 squared for the van. Okay, so this would have worked out to be 1,000. Let's go back to it. Okay, so that will have been 10 times 10 times 5,000. That would have worked out to 500,000. Okay, so this is 500,000. Sorry about that. So this is 500,000 joules. Okay, then for the car here, it's 15. This is when we have 15. Okay, so 15 inside there, 15 squared. Okay, 15 squared, and that will be equal to, okay, let's work that out quickly. It's going to be 15 times 15 times 2,000 divided by 2. Okay, divided by 2. So we have it as 225,000. So this is 225,000 joules. Okay. Now, total EK equals 5,000 plus that one. Okay, 5,000 plus 225 is 225,000. It will be 725,000 joules. So that is the total EK before collision. Now, after collision, let's just have a look at it quickly. But if I fail to, now, we have very little time to do this, but what you need to do, you go and find for me EK total after, okay? Because I found before. So the change in EK will be given by EK final minus EK initial. And when you get that to be less, obviously you're going to get it to be less than the EK before. Then that tells you the collision is inelastic. All right.
Thank
That's
you
the end.
so much, TK.
Yeah.
Can I just ask you one thing?
Yeah.
Umatsoban is asking, would I be correct to conclude that the larger the wavelength and slit width, the larger the degree of diffraction?
The larger the wavelength and the smaller the width of the slit,
Okay.
the larger the diffraction.
I hope you got that, Mazobano. Thank you so
Yeah.
much for tuning in, guys. Until next time, we will see you. All the best for your prelim exams. Life sciences, stay tuned. We will be back. We're going to have life sciences straight after this. So thank you, guys. Bye.
Sure. Bye-bye.